models like so-called Euclidean minimums spanning tree, the EMST, designed to try to make mixing models a little bit more local in mixture fraction space. Okay. Well, linearity by construction it avoids this non-locality, except when you're splicing between one domain and another. So it has, to a limited degree, the artifact that just basic curl model or modified curl has all the time. You know, it's always taking big jumps in terms of mixing things of very different mixture fraction. What I'm saying is most of the time linearity is much better in that regard, but occasionally it does suffer that same artifact just because of the splicing. You bring dissimilar fluids into contact. And you know, there will probably be some applications for which this gives some serious artifact. For instance, mixing these two could result in unburned hydrocarbons that the real system doesn't emit, or what have you. So I wanted to point that out. And secondly, I want to just give you a preview of what Sigurd, I think it'll be on Friday, will discuss in more detail, that there are other ways that we can and do implement the geometry of these subgrid linearities within a 3D simulation, how they're structured and how they interact, just so you'll know that there's more than one way to skin the cat in terms of subgrid modeling with linearity and also with ODT. So this is what Sigurd is working on, and Terlife as well. One comment, first of all, is that this approach is equally well applicable in principle to closing a RANS as to closing an LES. There are some issues of physical interpretation, and you know, to what degree, if you're closing a RANS, you're going to miss some of the physics. I mean, those are good discussion points that we could pursue if you're interested. But what I want to do is just show you this generic geometry that could be applied to either LES or RANS. And I should mention, I guess, Suresh just told us today, I hadn't realized that some people at NASA have actually used his method, you know, the previous view graph we discussed yesterday, as a RANS closure for K epsilon. So you can mix and match different subgrid formulations. I'm showing you a second of two. There might be others, but these are the two that we've been working on. So you can mix and match subgrid structure and interaction with either RANS or LES. And that, you know, it could be problem dependent or a question of, you know, computational cost. So, I just want to indicate a little bit about the interactions here. So the basic concept here is that you're going to construct three distinct but interacting flow solutions, and in each one, you in this case, RANS control volumes are refined in one dimension, as indicated in this way. So you could think of the linearity as actually a stack of control volumes. You know, we call these wafers because we can look at them in 3D. They have very high aspect ratio, and well, at the resolution, you can't tell with the pixel resolution here, but this also has a lot of streaks basically, and likewise, you know, with the blue. So any one control volume, looking at from that perspective, this is the same control volume, but in three different flow solutions. And in each flow solution, the LEM spatial refinement is present in a different direction. And this rendering just shows you some notional scalar property fields that could be resolved, you know, along each of these three. Now, having shown you this, I just want to give one more detail here. Associated with this geometry is a coupling or interaction procedure. Remember on the previous slide with this method that these splicings were driven by the LES, or equally well RANS prescribed velocities or mass fluxes, depending on how you're formulating this. Let's take them to the mass flux. You know, it's basically the 3D solver prescribes mass fluxes, and they dictate how much mass actually crosses you know, a control volume face during the given time step, that's still the driving. That's still the information that drives the interaction between the domains. And here are the same kind of arrows representing information from the 3D solver. Now, what we do in this case is, this is a 2D example to show, in the RANS context, these could be mean flow velocities. So what we literally do is try to take this domain starting upward, you know, from above this control volume, and say that we have to apply a certain displacement to represent this flow as dictated by the RANS, a displacement downward of this region of the LAM domain, and here it says we have to displace upward. But in this example, we're not limited to incompressible, but this example is incompressible. Well, if we do that, you can see that we're just going to accumulate more than the allowed volume within this, within more than the allowed amount of LAM fluid within the control volume. But of course, we also have to match the horizontal, which in this case is a net expansion. Okay, so if you displace from here by a large amount, displace by a small amount, you'll create a gap. So what we do is we take the extra fluid, we take just enough fluid to fill this gap, and we take it off this vertical domain. So here's this chunk. We rotate it, and we just plug it into the gap that's formed by displacing fluid from here onward by this small amount, and from here forward. Well, actually, we do the cut. This red line shows the cut. We actually cut at the center line here, displace this forward a little bit, and from the red line forward, we displace a lot. And then we've created a gap, and this shows both the gap, and it shows how we filled it in by taking the, so to speak, excess fluid from the vertical domain, rotating it, and plugging it into the horizontal domain. And it exactly fits because the field that we've been given is exactly incompressible. Of course, we have to be careful about that, because in this picture, now we're talking about a uniform mesh, so we always work in exact increments of the wafer thickness. There's the LEM resolution scale. And so what we do is, we call a banking. We take the fractional amounts that we can't implement, and we save them and catch up to them at a future time step. So we're always a little bit off just with that, that's just kind of a numerical jiggle, but we're always staying within a tolerance of the prescribed flows. So now this is different from the method in the previous view graph and the one we discussed yesterday, in that every LAM domain has a definite orientation. It's fully Eulerian. There's no sort of abstract, coordinate system floating around. So it's different in that sense. But it's similar in the sense that the splicing still has that same limiting characteristic, that when we plug this fluid in here, in general, we're bringing into immediate neighbor contact dissimilar fluid elements. Okay, so you can see that there are certain aspects in common to these two methods, but in important ways they're different. So let's see what else I can comment on here. Well, Sigurd will talk about some of the experimental comparisons with the constant property version of this, and so this shows some of the ideas that we're looking at. Of course, this is being taken to full chemical thermal expansion treatment, analogous to what Suresh has implemented. And another idea, I mean, this would also work with either method, Suresh's splicing or what I just described, to construct a subdomain. And this is actually very easy to do with just commercial mesh solvers. Construct some cuboidal subdomain in which that LEM, the structure I just showed you, we call it LEM 3D. That structure, or the or the separate more Lagrangian type approach of Suresh could be implemented subgrid, just to do it in some subvolume where the mixing and reaction is crucial. And so if you have a large system that has a lot of other processes that you want to simulate, but they're far from the reacting region, so you don't need the extra cost of the LEM subgrid resolution, then we would just have some matching conditions such that in here we're running a subgrid LEM, and and in here we might be running EDC or something as a subgrid, so it'd be cheaper, and we could be running, this could be influent or what have you, so that we can get the resolution of the physics in the crucial subvolume where it's needed without the cost of putting LEM 3D through the whole volume. Also, you might have complicated surface geometries, and well, this is an important point comparing the two. Suresh's method is general in the sense you can use it in an unstructured mesh. I mean, it could capture geometry. So if you need to be capturing details right near a curved wall or something, then there would be some benefit to using his approach. Whereas if you really need the detail just in some interior region, you could do this with either of the two methods. And well, another thing, since we're mentioning near the treatment near a wall, another closure approach. Well, I have some view graphs about this, but I'll just draw it. If you have, of course, we've been discussing mostly LEM yesterday and today, but on Friday I discussed ODT. One of the uses of ODT is to simulate wall boundary layers, and ODT captures the wall boundary layer structure. It has viscous layer, viscous sublayer that rolls into a log layer, and you can see the buffer layer in terms of when you look at the fluctuations, the velocity fluctuations, they peak in the buffer layer, rolls it over into a log law, and then it continues to a wave-like region. And it's very important. In LEM, you have to tell it all the turbulence. What I just described to you in the boundary, that's all an outcome of ODT, because the same way that you can understand intuitively why ODT produces a Kolmogorov cascade with -5/3, the same kind of dimensional reasoning. I mean, Prandtl didn't start from Navier-Stokes equation to reason about the log law. He started from simple mixing length ideas. Well, mixing length ideas are embedded in the so-called rate expression that decides the likelihood that a given eddy happens. So you can actually reason step by step about ODT as if ODT was its own world, and apply mixing length, just sort of qualitative reasoning to think about its own behaviors. Well, actually, I should show this out. I have it right in my. And you can understand why ODT would generate this. So here is Couette flow. So the symbols are experiments at 2 different Reynolds numbers, and the curves are ODT. That's the mean velocity profiles. And then when you take the ODT data, and of course with ODT you can afford to run so that the output of simulation curves end up looking as smooth as if they were theoretical curves. So this solid over here is the ODT result. This dot dashed is just the viscous scaling. Okay, U plus equals Y plus. But this is what it looks like on semi-log. This line is a log law.
How you manage viscous sublayer with your model?
Okay, here's
because there are some structures which are quite different from these triplets.
What happens? Okay, this is a very crucial point. So how does ODT represent a wall? it's very simple. If you try to do, you're not allowed to do a triplet map if this is the wall that penetrates into the wall. Okay? So what you really have to think a little bit about the phase space of the eddies. In other words, when we speak of an eddy rate, or likelihood of occurrence, frequency, the given type of eddy will happen. So what we actually have is a rate of eddies. We have an eddy rate distribution, we call it. So, okay, let's say this is the y direction again. Okay. So we have a rate lambda as a function of, well, y naught is the lower bound of the eddy. So the eddy goes from y naught to y naught plus some size L. Okay. So we have a rate y, L of y naught and L, lambda of y naught and L, which of course is a function of time, because every time the state of the system changes, since it really depends on the entire state of the flow, this is time dependent. And so the actual, if you want to say what, so the way to interpret this has units of 1 over length squared times time. So if you want to actually get a rate, you have to take a dy times a dl. So then you get something with units 1 over time. And the important point is that the time scale that you get for a large eddy is the time scale for let's say you have an eddy of this size. So the eddy turnover time for this eddy, of course, any one eddy is an event of probability 0 because no eddy is going to be exactly, these are continuous variables, so no eddy is going to be exactly at a given point y naught and have exactly some size L. So if you want to say what is the quantity that will scale like the turnover time for a size L hat eddy, it's basically lambda times L hat squared. This is going to go like, I'll call it tau sub L hat. This is going to scale as the turnover time for a size L eddy. So basically, this turnover time represents the time until you'll see some eddy that some member of a class of eddies whose size varies, say, it can vary within order L. In other words, that turnover time is a time until you'll see with y naught itself being anywhere in this range, from, so y naught can be in the size L hat range, and the eddy size itself, of course, can vary, like from L hat over 2 to 2 L hat. Just to give you an idea that the actual eddy turnover time tells you what is the mean time between events for some subclass of eddies within a given range. And so if you're looking at eddies very close to the wall, what happens is that a large eddy, the likelihood for an eddy of some size L hat to have its y naught between 0, let me just call it delta y. The likelihood that the y naught for a size L hat eddy will be between 0 and some delta y much less than L hat, well, that likelihood is going to be much less than 1 over tau sub L hat, because, in other words, it's a phase space argument. And so eddies of a given size are likely to happen only with in other words, reasonably likely to happen only with a standoff distance from the wall basically of the same order as their size. It's just going to be rare from a statistical viewpoint to have a size L hat eddy, but it gets much closer to the wall in terms of its closest approach to the wall than size L hat. And there's And in ODT, there's enforced a smallest eddy size. I mentioned on Friday there's something called a viscous penalty that says if an eddy has a size, if it has an eddy Reynolds number that's smaller than some order unity number, value that might be order of 10, for example, then the eddy can't happen. So in effect, there's a built-in viscous criterion for the smallest eddy. And as a result, that establishes a smallest size below which it's very rare to have an eddy, and that in effect becomes in the model the viscous sublayer. What I just described to you are some general inputs to ODT. They're not specifically designed to describe the wall in particular, but one consequence is that a viscous sublayer develops. And then if you develop this reasoning in terms of saying at some given y that's far enough from the wall so it's larger than eddies that can happen, then the dominant eddy that will cause transport at that height y turns out to be eddies with size L hat of order y, because the L hats that are much larger, again by the phase space argument, they're very unlikely to penetrate. If an eddy is much larger than L hat, it's very unlikely that its lowest point of approach to the wall is a lot less than L hat. It's not impossible, but it's rare. So in eddies much smaller than L hat, well, they can't contribute as much to transport as eddies, I should say eddies L hat much less than y can't contribute to transport as much as the larger eddies of order y. So the bottom line is that size y eddies are the dominant eddies that do transport a distance y off the wall. And that is simply a different way of restating the Prandtl mixing length hypothesis, which is that the mixing length is proportional to height y. I'm saying the rules of ODT, in essence, for this particular flow, reproduce the behaviors, on a local scale. And this is all manifested by the sampling of eddies, not arguments about, mean behaviors. But through the orders of magnitude of the likelihoods of different eddies, they end up enforcing within ODT the same picture as that Prandtl used to come up with the log layer. So that's why ODT has a viscous sublayer that rolls into a log layer. Then we can look at other things. These are fluctuation statistics. So this is velocity variance profiles. And for those who read the email this morning, the question was, how quantitative, how accurate is this? It doesn't lay over the curves. You can see that these are the measured profiles. These are somewhat lower. But part of the point I was making yesterday is if ODT can be, or LAM can be, to do not only this problem, but can do advection, diffusion, reaction problems with multi-step chemistry and extinction and all the flamelet regimes with not too much worse than this accuracy, then that's a significant capability. So, I'm not saying it lays over curves, but it comes into the right ballpark for a wide variety of problems. Here's, for instance, there are models that can do a reasonable job on velocity variance, but they can't necessarily address higher order statistics because they're moment methods, and so they only go up to a given moment order. ODT is a simulation, so you can go to to whatever order is of interest. So this is the turbulent kinetic energy balance in the same Couette flow that I showed, and on the right is the positive Y is showing the ODT results, and negative Y is just kind of a mirror image DNS. So, it's showing you it's behaving reasonably. In other words, by having gone to some further higher order statistic, there's not really a loss of fidelity relative to the lower order treatment. And I guess what led me to mention this boundary layer issue, the way I started on that path was I was commenting on near wall behavior. So one thing that we've implemented is a large eddy simulation with an ODT near wall subgrid closure. So you have an array of ODT domains that are vertically oriented. They interact laterally with each other. They also have a coupling to an LES, and so they provide a near wall closure, and we have some results for channel flow that shows that, you know, when used as a subgrid model, it gives close to the wall a comparable quality of.
So you mean that this can be used to replace ordinary wall functions?
Right. Yeah. Now, even in cases, now there are cases where wall functions may be sufficient, but
wall functions are very bad for LES.
Yeah. Well, you know, people are even. What I want to comment on is LES of what flow. If we're talking about a statistically steady channel flow, yeah, there's an issue in itself. But even if someone had something that they felt for their purposes did a steady channel flow, what about problems where you have some transient in the bulk? If you're doing the atmospheric boundary layer, the prevailing wind is to the west, and then in some short time it turns to the north. Well, the boundary layer doesn't respond to that instantaneously. There's some time lag, and in between there are some very anisotropic things going on in what was previously the log layer. And these wall functions aren't going to tell you about how the turbulent transport over time transmits the change in the bulk, the bulk flow momentum forcing toward the wall. But ODT has that time lag response within it.
Is it ODT has some chance to include these anisotropy structures?
Well, it's important that ODT in itself cannot see things like the streamwise vortices. Okay, so it's still a model that's idealized. You know, that's a whole. When I call it Picasso turbulence, it can't see that level of detail, and things that are sensitive to that level of detail, won't be represented. But of course, we know that the basic structure of the certainly of the mean profiles is based on simple considerations that don't have to take that into account. We know the reasoning. Prandtl's reasoning is enough to explain the log law. Of course, there's other more sophisticated nuances, but the bottom line is he came up with simple reasoning that explained the log law, and when the rate expression based on similar mixing length ideas is used in ODT, it reproduces that. So, but of course, if you had some, say, reacting, let's say you had some kind of flame wall interaction, I can't tell you with certainty or high confidence that ODT lacking the streamwise vortices and so on, the near wall structures, I can't tell you with high confidence that it's going to give you a very accurate result consistently. However, what I'm proposing is that errors in the detail of effective structure are probably order 1 errors in terms of how they impact the diffusion reaction processes, chemical rates, and so on. However, models that average over or filter over the small-scale spatial structures when you're doing mixing closure, losing flame structure and so on, they can give much bigger than order 1 errors because they're missing the entire dynamics of how an individual flame surface responds to the wall flow perturbations and so on. So in other words, in some sense, errors in the structure of the advection, I would expect in general would be more benign than errors in treating the way an individual structure of a flame, is responding to its surroundings or to other nearby planes. But this all has to be tested. I mean, we have various tests and examples I'm showing you, but you know, case by case, we build up confidence as we understand what the model can or cannot do.
What are the controlling parameters when you implement ODT?
Yeah.
For near the wall, do you need to have something wall shear stress? But this is computed.
It's computed, yeah, it's an outcome.
It's just a non-sleep boundary condition, what you need?
Yeah, right, but that's what a DNS needs too.
Of course.
Yeah, but as far as parameters, it's very important that that in writing this rate expression, and I showed a view graph on Friday that gave some of the physical reasoning behind this this frequency of eddies of a given type, that the mixing length reasoning can only give you proportionalities. So the crucial parameter is just a prefactor that has to multiply for those proportionalities to give you the actual rate. And that prefactor then dials the overall eddy rate. It's like, from the eddy viewpoint, running the movie faster or slower. Just getting more eddies. Although that's too simplistic, because if you run the movie faster, you get the same flow. It dials the eddy rate, but of course, the viscous advancement and so on is fixed in time. So basically, it's the overall frequency of eddies that's running faster or slower. So there's one essential parameter, which is that one. For this, now, in order to do a good job on this flow in particular, I mentioned that you have to have a threshold eddy Reynolds number, otherwise you don't really end up with a viscous sublayer. Well, you can get a viscous sublayer but for other reasons, but you might not end up getting, in particular, the right. I guess the crucial point is that in order to do a reasonable job on these variance profiles and have the buffer layer in the right place, you have to set a reasonable value of the smallest eddy Reynolds number for which you would allow an eddy. In other words, if you have I mentioned yesterday that like if an eddy's interacting with a scalar, sometimes if low Prandtl number, that could be unrealistic because the eddy happens, whereas if it was a scalar, it never would have even, if there was strong scalar diffusion, it never even would have allowed that perturbation. Well, in the same way, it's important, especially in ODT, to prevent eddies that couldn't happen because of viscosity. In other words, if you take a given velocity fluctuation, if you have like in a 3D flow, an eddy of size L that's trying to develop for some given L, and if there's some delta U, this is the velocity differences driving the eddy. If that delta U over L times L divided by the viscosity, if that's less than some minimum or threshold Reynolds number, then viscosity won't even allow this eddy to turn over. Okay, so that's basically the Kolmogorov concept, right? Yeah. So in the rate expression, of course, we have viscosity in the separate process. Between the eddies, we're running viscosity all the time. But we also have to recognize that viscosity plays a role in preventing eddies below a certain size. Strictly speaking, they're below a certain Reynolds number. So we actually have to enforce the Kolmogorov microscale based on local conditions. It's not sort of a global microscale. We have to enforce it within the rate expression so that we don't get unphysically small eddies below the Kolmogorov scale, because if we didn't, we wouldn't have the buffer layer in the right place, and we wouldn't have the turnover to the viscous sublayer at the right value of Y+. So this threshold Reynolds number is an empirical parameter. So that's something that, especially for boundary layers, we have to adjust that as well. So for boundary layers, we have two adjustable parameters.
I wonder, in the ODT, you solve the Navier-Stokes or the viscous momentum equation. You solve, right?
Yeah, right.
And then you have the viscosity.
Mm-hmm.
This will somehow, if you have two small scales, it will smooth it the way itself.
Yeah, yeah.
The model.
Right. Do you see, but even though, you know, if we let arbitrarily small eddies happen and then let viscosity smooth them out, it would still end up with more fluctuations than if you prevented the eddies
Yeah.
from even happening, you
Yeah.
see. So that's,
It takes time. Maybe, to
right, it takes some time for them to smooth it out. It may be very quick, but still, it's not as accurate as preventing the eddies that are too small to really happen physically. And it's also a computational costing. Even if it doesn't have much impact on the answers, it forces you to resolve smaller time scales if you do those smaller length scales, if you do those smaller eddies.
Yes.
So if they're not physical and they add to the cost, you want to get rid of them anyway.
In one of the slides, I still do not really understand what you really do. In the slides number 20, there you have some lines where you do spacing.
Yeah.
You
Let's see.
number 20.
Oh, okay. Yeah.
Yeah, here. I guess student over there, they may also have the same question as I do. You have these lines. What are these lines? Do not mean so much. Just a representation of something.
Well,
It's not a direction. You don't solve something on the line along the line.
the line actually is a segment on which the linear eddy model is solved. It's really no different than what happens here on this. That line, these same processes are happening on that line as happen, you know, along this linear eddy domain, except, you know, it's a smaller piece. It's only a piece that large. But within that piece, it's doing the linear eddy processes. It's just, in this picture, that level of the model isn't shown in this picture. This is just showing that there's some, linear domain of a certain size. What this picture is not showing you is that this linear domain has property profiles on it, fluctuating property profiles. And those profiles are being diffused, and chemical reaction is happening, and triplet maps are happening all over this line.
Being a CFD people, we usually think about the greens. Inside there are a lot of two-dimensional greens.
Well, but how about Lagrangian models?
Well, I guess the big point is that that line is an instantaneous orientation of the line. In other words, it's actually taking snapshots of the subgrid picture. That's if let's say if you're doing a cliff image of a flame structure, you do a laser, you get a laser signal, right?
Yeah.
That's what I kind of try to explain it as instantaneous images of the subgrid scalar structure.
And this
Also,
also
we use images of CH or
along a multi-component
Yeah.
species.
Yeah.
I guess one way to sort of address this question is, does the orientation of these lines have a meaning? I think that's probably where, is that what?
well, the
So
proposal.
the LEM solution is on these lines, but these choices of all those orientations, does it have a meaning, or
Yeah.
the choice is arbitrary?
Well, if you had a control, this is a general LES issue. What is the universality and the degree of isotropy of the subgrid scale? Let's say this was, a 2D image of a physical control volume, physical volume from a flow. Okay.
yes.
Well, if you took a line of sight, like with laser imaging or something, if you took this line of sight and looked at the statistics of your scalars along that line of sight.
Okay, line of sight. Okay.
Okay. Let's say you took statistics along this line of sight, okay?
Yeah.
If statistically you couldn't make a distinction if you gathered data along this line of sight or along this line of sight, then you'd say it doesn't matter what line of sight I take. Either one of them is a representative sample. So I'll just define, as I mentioned yesterday, I'll just define some hypothetical coordinate zeta, and I'll say, you can think of it as this one, you can think of it as this one. If this is isotropic, it doesn't matter. If it's anisotropic, well, any subgrid model that assumes universality has some issues with it. But so the model is at this scale of the individual control volume, assuming isotropy. So we say, well, we'll just have a line. It has a hypothetical coordinate, zeta. But you can think of this coordinate as living wherever you want within the control volume, because the laser image of the property profile along the line of sight, I'm supposing, doesn't care whether you look this way or you look this way at this small scale. Okay, because this whole thing is just one control volume. And so then we say, we're going to run linear eddy on this, and we may start at the profile looks like this, and the linear eddy will evolve it to some other shape, and so on. So it evolves by itself for a while, but eventually we get to a time scale where the transport on the linear eddy, or the transport in general, the physical transport, is of order of the control volume size. So now it's no longer valid to just run linear eddy like an isolated object, because we're at a time scale long enough so that much of the fluid would have moved from this control volume to its neighboring control volume. So we have to represent that larger scale of transport on that longer time scale. And the way we represent it is to say that this control volume has its sort of representative line of sight on which we're doing linear eddy, and it doesn't really matter, or we're assuming that it doesn't matter based on isotropy, what the orientation of it is. And this neighboring control volume, has its own, well, it should make it, this is actually supposed to be the domain. So yeah.
Give yourself 2 minutes because we need to switch to
Other topics.
other topics.
Right, okay. And this one has its own, call this zeta 1 and zeta 2. But now we've waited for a long enough time so that typical displacements by transport are this size. So we have to represent that. In other words, time scales where it's no longer valid to think of this or this as isolated. So then we start exchanging material, taking some of this material, putting it here to represent this transport.
So this time has to be quite large.
Well, it's the large eddy time. It's the CFL time for the 3D coarse-grained cells. Okay, roughly as an estimate, which is a lot larger than the time scale associated with the Kolmogorov microscale, which is what the LEM resolves.
I have a question. Along this line of sight, is this one-dimensional transport equation of the reaction diffusion term, is that solved along this line of sight?
Along this, on each of these domains, yeah. The
Okay, so you're at least doing the reaction diffusion
Yeah.
along those lines, and if you can imagine that the flame crossings are actually, it'll show up as flames, because if you're a flame or a scalar gradient. So you're recovering the stirring. One way to think about stirring is recurring the wrinkling of the flame at the small scales, not the large scale. And then the diffusion is smoothing it back. So if you had one stirring and say 100 diffusion, pretty soon they'll be all wiped out. There'll be no, it look like a flat flame. There's nothing there.
But then if you do this splicing, then you have discontinuity initially.
Yeah, but there's immediately that that's the then you have there's the diffusion will smooth it out.
Yeah.
Diffusion, yes.
But that was my first point, which is that those discontinuities can be discontinuities where you have cold fuel meeting cold air,
Yeah.
which may not be accurate.
So some very specialized cases, this will not be a valid problem.
Yeah.
The big confusion I think people have is that this is designed for high Reynolds number flows. It is actually becomes more accurate, in my view, at high Reynolds number than at Landmer conditions.
Yeah.
Because
Now
it's not designed for
Now, this business of discontinuity, it's important that standard mixing models create these discontinuities all the time. Because, like I said, Curl's model, it just assumes you have n basically pots of fluid, and it'll take any pair of those.
But they don't solve spatial derivatives. In their
Right,
model.
that is why they can't do diffusion.
Well, that's even worse, because first of all, they're mixing fluid of any two different mixture fractions. One of them could be deep in the rich zone, the other could be deep in the lean zone. They'll just mix them. Not only do they have the dissimilar fluids meeting, but they mix instantaneously. But the point is, every single time that they mix, they're mixing instantaneously, and the fluids are of very different composition. Here, this splicing only happens once at the large-scale CFL, whereas all the hundreds of time steps on the LEM is all local, diffusion controlled by the true resolved fluxes. So the artificial splicing in LEM is the occasional exception to the rule. In a Curls model, the artificiality is in the entire, mixing closure.
So I guess the other issue, coming back to the mixing point,
It takes a while.
It takes a while.
as you go to a higher Reynolds number, some of these errors that we're talking about is minor compared to the turbulent effect.
What do you need
So
to
it is, if like a lot of these flamelet problems that the people were talking about, these are actually low Reynolds number flames.
Oh,
So in some sense, these are based on pure laminar phenomena.
but I
This
can't
model requires an inertial range
use
spectrum.
my- I can't use it.
So if you don't have an inertial range, the
I need
turbulence,
an iron key. Someone else?
linearity should not be used. So my argument is that this is really designed for high Reynolds number flows. And if you go to like very low Reynolds number flows, you'll have to do very specialized treatments. Like you have a gradient, let's say, discontinuity when you slice, and there's no turbulent mixing, you get molecular numerical issues.
Seems to me this splicing has to be done locally according to the local property at a local frequency.
Yeah, it is done locally.
Local
Yeah,
frequency.
every grid, that's an LES grid, what he's showing. So it's done, it varies every grid point.
I mean, sometimes you do 2 time steps, you do 1.
Yeah, it's actually local, like some higher Reynolds number regions, you might have 100 stirrings and 10 diffusion, some places you'll have 10 stirring and 1 diffusion, but that is, those time scales are computed every time. So it's not a global, not even a CFL time. It's like a local time, But how far it evolves depends on the CFL time, before the next step takes.
All right.
Vladimir is not active today.
I'm going to steer the discussion a little bit towards the sort of the combination of everything, which is when you take LES with what I would call low-dimensional stochastic model, or one-dimensional stochastic models, and that includes LEM and ODT. When you combine the two, you basically have to deal with models for this, the different elements of this, and of course the different elements for this are the implementation of turbulence transport, which is stirring. And stirring here basically follows some basic rules that satisfy some observables that we're done with scalar mixing or turbulent combustion. So it basically follows specific rules. And I think Alan built these models intuitively, so instead of you don't necessarily start with the Navier-Stokes equations and try to come up with these rules. Those rules are based on basically intuitive ideas and observations. And then the important part of these low-dimensional models as well, because we keep thinking of triplet maps and that's it, but we actually have also this coupling, important coupling of reaction and diffusion that is essential in combustion. That's what makes a flame front. What makes a flame front is that what happens at the small scale, sub-millimeter scales. So that's an additional attribute to these models that you cannot find, say, if you just basically start with moment equations. You have to, you have to solve, when you do moments, you have to sort of reconstruct the effects of reaction diffusion, while they come naturally here, the solutions for LEM and ODT. And in that sense, when you're solving equations, conservation laws for these equations, you don't assume anything because you're solving, basically the thermodynamic state of the whole system in space. And of course, you have the issue of coupling, and that's an important part. Okay? And coupling is the issue, for example, of stirring large-scale transport. And how you split the transport from resolved and unresolved. And also the issue of geometry. You have 1D solutions that you're trying to basically place on a 3D domain that captures all the sort of the large-scale motions. And that's sort of an important choice to make. And sort of 2 examples that you can actually, or 3 examples you can actually imagine here, and I'm living here in 2D sort of domains here, that you can build ODT solutions or LEM solutions and LEM solutions, for example, residing within a grid. That's one way of doing it. Or you can build these solutions embedded on a flame. And that's a very cheap way of doing it as well.
But here you need to know the flame front, right?
Yes, you have to track the flame.
Track the flame.
So that's maybe a G equation, maybe doing a mixture fraction and identifying the stoichiometric value. It buys you, and also you are committing to what flame mode, what combustion mode you're dealing with, whether it's premixed or non-premixed. Okay? If you don't tie yourself to this, it's generic. It does not know a priori, you do not enforce a priori what combustion mode it is. But once you define a flame, you may actually also be committed to what regime you're dealing with. Flame-lit to sort of thin flame kind of regime. So that's sort of but it is one option that is fairly economical and computational. Okay? You don't have to basically put ODT or LEM solutions everywhere. So the other way of doing it also is to basically build sort of the lattice that, for example, that you see in LEM 3D, in which you basically are running ODT domains, basically running in all directions to cover statistics and gradients in all directions. This tends to be more expensive, but just because ODT can see boundary conditions, you can actually sometimes just cut off. You can basically attach an ODT solution only around conditions here where you have a quiescent or you have a certain mixture conditions and make them float. It doesn't matter. Okay? This is the Lagrangian approach because the flame is moving around. This is basically an Eulerian approach if you just have a lattice of ODT or LEM solutions, or basically I'm implementing it for ODT. Lattice of ODT solutions that basically capture statistics. This is either also statistical models when you get to that. This is not like filtered DNS. This is you basically building a statistical model. Okay? You're coupling low-dimensional stochastic solutions on a 3D to capture the physics that you're not resolving within those grids, within the subgrid or sub-filter kind of scales. Why do we need something like that? It seems like it's a little bit more expensive. Why basically not go back to the moment methods? And this is where the case I'm making here. When moment methods are good, use them, no problem. When moment methods fail, then there's no substitute for trying to compute or model directly the physics that you're not resolving. There's no substitute for that. Especially if you don't know ahead of time what problem you're dealing with. And then, you can get to surprises here. Traditionally, sort of back in the 80s, the sort of infinite sort of fast chemistry thing would be sort of the best way of doing it, But then we moved on to finite rate chemistry effects. How do you capture the effects of dissipation rate on chemistry, for example? And now we're moving on to something even more complex, with some non-equilibrium effects. When you have extinction, when you have reignition, when you have ignition, when you have things that are transient, that do not follow the standard statistics of the Gaussian distribution or beta PDF, log normal, all that stuff does not follow it. That's when you need to have a very, very interesting sort of direct way of measuring the statistics and also computing the physics. Okay? So moment methods, what do we do? So this is like Flayman CNC. You can think of PDF as sort of the ultimate moment method in a sense because it constructs all the moments. PDF transport equations. So the idea is that you base them on the transport of moments. Non-premix, you have mixture fraction. Premix, you can have progress variable. You can run with it the equation, get the flame surface density, whatever you're trying to model. And the idea is that these moments that you carry within or you compute within the CFD code are able to do two things. They will be able to construct for you the statistical distribution. That's important. They'll also be able to allow you a way to look up or solve for other scalars. Okay, so if you're doing a mixture fraction and you carry with it, for example, a variance or a dissipation rate, you assume you can actually access, Flamework library and then look up everything else. And the idea is that you want to keep the moments at a minimum, of course, because it's computational cost, but also for every moment that you have to transport, you have to worry about closure. That's an important thing, okay? Well, the limitations of moments, because you basically choose these things, is that you may be regime dependent. Maybe flamed, maybe distributed reaction, whatever that regime is. It also depends upon the combustion mode, whether it's premixed or non-premixed. Okay? Now, if you have partially premixed, which we may see a lot in combustors these days, you're going to have to basically increase the number of moments to do something else. The other issue, which is really critical, is when you assume a very nice shape for distribution, you don't worry too much about the outliers. What happens at the size of the distribution, when it looks like this, what's going on here may not be that important because it doesn't show up in equilibrium chemistry kind of conditions. But what happens if this outlier is an ignition kernel? Some non-homogeneous mixture like an HCCI, and then you have some of these things showing up in local conditions that depend also on the local dissipation rate, not the global NES result dissipation rate, but the local dissipation rate. How do you handle something like that? When you're just basically trying to fit a mean and a variance using, say, mixture fraction and say, dissipation rate. These are the issues that we have to really worry about as we move on to sort of new combustion technologies, where you worry about, you don't know ahead of time where your ignition is going to occur. You don't know ahead of time what combustion mode you're dealing with. You switch the fuels a little bit here and there. You may get to partial premix. You may switch to premix. You can change it to non-premixed. These are the issues where I think some of these models would have an impact. That's a niche, okay? If everything else works fine, if your moment method works fine, that's great, because moment equations look like, some of the Navier-Stokes equations. We're used to solving problems like these. Okay? So every time you improve these models, you have to add more moments, and then they become more expensive. And then you have to do worry about closure as well. Okay? So, although we are able to push the moment methods to a higher level, the question is there would be diminishing return. Diminishing return because you have to worry about making the computation more expensive. You also have to worry about closing things when you have reactive scalars as well. So if you add, for example, a progress variable to mixture fraction, you have to worry about the source term for the progress variable. So that's really what the issue is here. Okay? So what LEM-LES and ODT-LES are supposed to sort of provide is no a priori assumption about combustion regime and mode. Okay? Unless you choose to basically say, I'm tracking the flame, I'm putting all these solutions known to the flame. That's your choice. These models are designed to capture physics that originates on an unresolved scale because they are resolved. They are DNS-like resolved. Okay? And in contrast to sort of other models as well, you actually are, with that resolution, time scale and space, you actually are capturing reaction, diffusion, turbulent transport. There's a lot of coupling here, especially when you have finite rate chemistry effects or non-equilibrium effects. What happens to the history of the mixing and chemistry when they compete at the same time, you'd like to capture that so that you can get the physics right. Okay? And also you tend to capture large-scale transport with splicing, with what happens with the LM3D, what happens with LSOET that I'm doing. So there are sort of tricks to do that.
Can I ask a question?
Yes.
You said these are resolved, but it's resolved only in one dimension.
1D, exactly.
Then my question is, your vorticity is not going to be correct.
Well, in subgrid scale or large scale?
DNS sense.
No, what you're doing is you actually are producing the statistics.
Yeah.
You're not
question.
producing a DNS.
My question was not very good. I mean that this is not going to be very important to resolve these ADs. That's what you mean, right? If you
No, but it's
care
not
about
just the
statistics.
eddies. It's for example, the effective eddies even within the subgrid, the sub-filters and scales can be many. You can basically wrinkle a flame under the sub-filter. You bring flames together close enough and you generate curvature. That's an important
you
aspect.
separate them sometimes.
Exactly. So all of these effects for these eddies that are sub-filter are being taken care of by the stirring events, the triplet maps. They can bring flames close to each other. If the two flames are very close, they can interact, they can annihilate. And that's an effective curvature in the sense when you curve a flame too much, you can actually make the flame extinguish.
The final solution
Yeah.
of your LES, LEM results, do you satisfy continuity, momentum, species, energy?
The global continuity, from my perspective, the way I'm doing it, is done on the LES grid.
Yeah.
That's the one that sees everything. Okay. On the ODT domains, you sort of conserve stuff, but the global conservation, mass, momentum, and everything is taken care of on the LES grid.
Just like sometimes terminology can be confusing. ODT obeys, if you have, and like, talk about constant density flow, ODT obeys the incompressibility condition. In other words, the conservation law of all species and mass and properties. Some people, when they say continuity, mean the continuity equation, the rho dt, plus div rho v equals 0. Obviously, in LEM is not even a v, so it's not solving a continuity equation.
It's a line of sight. So if stuff comes in, if you have 1D domain and stuff is coming in and being pushed this way or this way, you know the counter.
Yeah, but it's still possible for a mathematical process to be conservative in the same sense that the continuity equation is conservative, even though there's no time stepping of rho dot plus div rho v equals 0.
Locally, you don't care about that, but globally, it is satisfied. When you do splicing, you follow the rules.
Yeah.
So there are different enforcements at different levels.
Sorry.
Oh no, please! This is the reason why.
What's the whole point?
Yeah, that's the whole point.
And, my question, in fact, if we analyze the acceleration, acceleration depends mainly on the pressure gradient. It's not viscosity.
Yeah.
Maybe implicit, but directly, if you measure the turn by turn, the gradient, acceleration is determined by pressure gradient. In ODT model, there are no pressure gradient. How we break up the physics and nevertheless describe something?
Okay, the treatment of pressure is one of the key points. It's very subtle and there's many aspects to it. First of all, there's pressure at the large scales that ultimately drives...
I skip pressure gradient.
Right, pressure. Well, okay.
It's not small. It's not large scale. It's small.
Well, they're at all scales. Okay, so let me. I just want to take it step by step. The large-scale pressure gradients are ultimately what create the gross motion of the flow. Okay, so that's going to be resolved on the LES grid. So now we come to the pressure fluctuations. Now, in general, turbulence models don't really capture the causal relation. In other words, any kind of closure, what have you, it doesn't capture the mechanism of fluctuating pressure interacting with fluctuating velocity, it actually captures outcome. One example is the return to isotropy model, within second order closure. Okay, so in essence, a pressure velocity correlation modeling is a modeling of outcomes of an interaction. It's not the modeling of the process of the interaction. And one can argue that the triplet map is ultimately reflecting an outcome of an instability associated with what's ultimately forcing by pressure gradients. Now so I think that the best way to put it is that we have a model that's based on our empirical understanding of the outcome of pressure velocity interactions, which is really what any closure model does in dealing with those interactions.
No, I'm a little confused. Exactly, the pressure, Vladimir, you're talking about fluctuations at the small scales? Or?
Well, it's just small
Instantaneous
scales.
pressure.
Instantaneous.
Yeah.
I mean, of course,
But due to density variation or due to acoustics?
well, you could take the zero Mach number. There's always a pressure. There's always a pressure Poisson
I
equation.
can write maybe this
It's a
equation.
force. It's an applied force.
Right. Yeah.
In fact, if we write this equation for
Yeah.
It's just Newton's second law. I mean, it's acceleration is equal to the applied force.
Right, okay.
so it's the main term.
Right, okay.
It's very known. In fact.
Yeah.
If Reynolds number is huge, the term is the most important.
Yeah.
And there is a big difference because this term is potential.
Okay. Well,
Right.
let me actually give you an
This
example.
term is exactly inversely. It's not potential. So how we can describe with triplets?
Well, let me give you one example actually of how the model actually contains. Let me see if I have it in the talk I gave on Friday. Let me see where that was. Oh, here it is. I'll have to borrow your.
This equation is even for incompressible case.
Yes.
It's a Mach number.
Yeah, that's what I said specifically.
There are no acoustics.
Yeah, right. Just want to see where I had that example of them. Describing all these here. Just jumping around to find the. Okay. Here, I'm commenting here on pressure velocity coupling. Okay. In ODT, there are two operations. One is the triplet map. You apply it to all the fields. Here's a U, V, W, and a scalar. And the triplet map is just carrying fluid elements and all the properties they contain. But pressure has other effects. One effect of the pressure is to part of the acceleration that the pressure applies to the velocity field rotates the orientation of the velocity vector. As a result, energy that is in one of the velocity components gets transferred to the other. At the small scales, the rotational effects of the vortices in effect cause a loss of knowledge of the laboratory frame of reference, and that's why the finer scales become more isotropic. So a way of reflecting that is to, now in this particular example, the U velocity is taken to be linear, but V and W initially are just taken to be zero, just for an example. So here, we apply an additional operation that modifies the U velocity. It's no longer a map now, it actually is adding a function to the U velocity in order to change the U profile and take out some of the kinetic energy, but still in this case conserving momentum, put some of that kinetic energy into the V and W profile. So from the viewpoint of ODT, this is the ODT version of return to isotropy, which of course is a model of pressure-velocity coupling. That's, I mean,
This
conventional.
is in a statistical sense, but you know that if you measure the velocity,
Right,
okay,
yeah,
in fact, acceleration,
Right.
you know that acceleration, the modulus of acceleration,
right,
is very well correlated. So
Yeah.
the direction is stays in some direction very long time.
right,
It's just the velocity which rotates.
yeah.
So this,
The model's not capturing that level of
nothing,
detail.
nothing of that.
The model's not capturing that level of detail, and any outcomes or observables that are crucially dependent on those features will probably, reflect some discrepancy. I'm not sure what observables in a statistical sense are sensitive to those features, but if there are some, then they will probably. They'll be
As I understood you say that due to pressure gradient, you have the change of orientation.
Yeah, but we're not seeing that.
After it's viscosity
Right.
goes.
Well, the point is, the model doesn't have that mechanism built into it. This is just a representation of one known outcome of that interaction. Just like in second-order closure, you have the return to isotropy term. Doesn't model in detail the fluctuation. It's a model that's saying, well, we know one of the outcomes is the return to isotropy, so we'll just put in a model that forces the return to isotropy, but we're not going to capture all the details. The same thing here.
But the reason of my question is follows.
Yeah,
There are a lot of efforts to do DNAs.
right.
So, if we can describe something for applied, problems,
Yeah.
with very simple models,
Yeah.
nothing to know about what happens with the direction of acceleration, so why we do so much efforts
In the DNS?
in DNS? What information we take here from DNS?
Well, for combustion in particular, what's important in DNS is that the DNS fully couples whatever advection it resolves with the diffusive transport and the chemical reactions. So for combustion,
I agree.
that's what's important. It's not important for combustion, I don't think, that the DNS is seeing a particular correlation between pressure fluctuations and velocity fluctuations.
My question,
Yeah.
what information maybe you can take from DNS and to use in your models? At the moment, I see nothing. There are
That's right.
no information.
That's because I'm
Why?
trying. The reason is because I try to build a model on empirical principles that are of sufficient generality so they don't depend on the specifics of one flow versus the other. The DNS can give us two forms of information. One is information of a general nature, but over our hundreds of years of studying turbulence, we probably already know that stuff. The other is the DNS can tell us the specifics of a given flow. If I put the specific information into the model, it'll be a great model for that specific case, but probably that additional information will actually be misleading when I apply the model to a different case. I want to keep my assumptions minimal so that it's general rather than putting in more special case information to make it great for one case, but then I do another case and
What can you, what parameters, what information from DNS you can use to improve your model? What kind of information can be useful for improvement of your model?
I think it's like any other model. That's validation.
No, but
It's like any
Well,
other
for example,
but what is-
moment models, we know that
Yeah.
we have to modelize this term. But here, I don't see what term we have to improve using this
Right.
kind of DNS.
Right.
It's not clear here.
right. Well, that's the point is that this is not a model design. You see, this is a very different approach from closures, because closures, you have a higher order, there's a lot of terms to close, and people trying to just keep improving closures. This model is not a continuous improvement concept. This model actually tries to put us, I would call this model a discarding of information model rather than an input of information model. You want to take out, you want to sidestep all the particular details and just take a minimal set of concepts that are hopefully general and just see what they give. Because the cases where there's some very particular thing going on in buoyant flows, there are lots of examples. For example, okay, here's a very good example. I mean, whether or not I knew from DNS or experiments, if you're doing stable stratification, there are gravity waves, okay? And I don't see them in here. I've thought about various empirical ways of kind of hardwiring in some gravity waves.
Should we continue the discussion and maybe individually?
Okay.
Can I say just one phrase?
Okay.
Can I tell that, in fact, formulate what you do?
Yeah.
How far we can go from very primitive, in good sense, from very primitive formulation of picture products.
Yeah.
Can I formulate like that?
Absolutely.
Okay.
Good.
Just a question or remark, you can still improve then the eddy distribution and steering frequency.
Well, that's in linear ready.
Yeah, also in ODT or not.
Well, ODT, you write down a rate expression, and it determines at any given instant all these properties.
Yeah, but you can still tune how fast it eddies are.
Well, there's a parameter in there. That doesn't change the structure of the formula.
No, okay.
Yeah.
But you can still improve that.
Yeah, you can look at issues like that. I wouldn't say that that's beyond improvement, in fact. And there are other things. If you want to put in surface tension or other effects that are not in there, you can add something to the rate expression to treat that.
Yeah.
Yeah.
Because I was wondering what happens with the passive scalar if you tune or change this parameter. What happens with the intermittency? What happens, for instance, with the scalar spectrum? Because you have something like you have the creating spectrum and the bachelor spectrum.
Yeah. Oh, well, that's a whole topic as to how the
It's a bit
outcome.
fundamental, but we're well interested to use ODT for that.
Yeah, oh, definitely. Well, I've done LAM with seeing the bachelors in the, the inertial range, the viscous convective, and so on. So I've done that with the passive scalar for linear ready, yeah. But to do parameter studies is important too, and I think Suraj has done some of those as well.
Yeah, but it's diffusive dissipation range. We have them with the bachelor spectrum, we have K squared fall off, and with the creating spectrum, we have K fall off explanation. I was wondering what do you get with ODT, and does it change when you change this rate then?
You're talking about the dissipation range.
Yes.
The dissipation range. Okay, so we have to talk about each. Now I have to talk about it as a function of Fresnel number and so forth. In any case, there is a strong fall off. It's not. It's hard to see if it's whether it's exponential or some power law. Depends on some details of the parameters in the dissipation range. But in either case, it's a strong fall off. But there are some details that depend on Fresnel number, whether you're talking about ODT or LAM and so forth.
Yeah.
So I think that would be a good kind of more kind of specialized discussion of some
Yeah.
things there.
Did you show this on Friday? If you showed it.
Well, it was on a view graph, but I wasn't referring to it.
Okay. So I just wanted to sort of discuss briefly how ODT, rendering of sort of important effects of combustion is done. This is actually standalone. You can do ODT standalone for simple flows, but otherwise you have to couple it with LES or RANS for more complex flows. This is the 1D solution. It's the horizontal lines, and then the temporal evolution is interpreted as a downstream distance in a jet. This is actually Sandia flame, which is basically a piloted flame with fuel, the pilot, and then co-flow. And the sort of dashed lines here, horizontal lines, correspond to eddy events. So you're running this, basically deterministic reaction diffusion equation, and on top of it, you're doing stirring events. So you have your solution happening here, and then when you have a stirring event, you basically change some of the local profiles within the stirring event, and then you evolve your solution reaction diffusion equation as well. Okay, so this is an evolution in time. And of course, the ODT will respond to where you have, say, for example, this configuration high shear. So at the interface of the fuel and the cold flow, and also the cold flow and the exodozer, you're going to get your first stirring events. The stirring events will grow in size. That's an additional ODT parameter for standalone that is used to do that. And then behind large eddies, you may actually generate enough gradients as well to also sustain smaller eddies as well. So you can see some level of cascade going on here. The important part here is really what we're seeing here as far as the OH profiles as you come out of the inlet and then evolve downstream. There's a region here where you actually, because of stirring events, you get to conditions where you basically generate high enough dissipation rates to actually locally extinguish the flame, and that's what's happening here. And then eventually the stirring events will bring in sort of dormant kernels within right downstream there to generate reignition. All of this is done within sort of a 1D solution. So that's how the whole process is sort of rendered within a single simulation. That's what the ODT solutions are going to be done. But you can average the simulation, then you can see sort of you have to take different realizations based on the history of the random numbers. You can get also an average simulation in which you can actually see also extinction and reignition going on at the same time. So this is sort of a standalone, meaning it's not really embedded in any LES or RAS.
Can I ask,
Yes.
You have a lot of small dots
Yes.
in this one.
These are really small eddies.
These are really small eddies.
Yeah, I mean, small eddies, not really, I guess it's all relative.
Is it in several grids or in one grid?
No, they occur over grids. I mean, the minimum would be, for example, to have, because you have the triplet map.
Yeah.
The triplet map means you actually generate 3 copies and revert the middle copy. So you have to have resolutions within those triple, the 1/3 of these resolutions.
Also, I don't know if this was part of the question. This is all on the same domain.
Yeah.
I'm going to explain the marching.
He said it, but it's not LES. So
Yeah,
it's
this is
just
not
one
LES.
domain across the
Yeah.
And he's
lateral
it's as if the domain, in other words, as he's time advancing the domain, he's
evolving
basically interpreting that as moving streamwise.
It's like a jet,
Okay.
it's a high-speed jet.
So in other words, this is actually the solution of one ODT time
over
advancement,
one sweep.
but it's kind of been laid out and swept out as if it was spatial advancement. Now there is an ODT formulation that actually uses the spatially developing equations rather than time developing, which obey the different conservation laws, and we've been using those as well. As far as the question if there were is there one or multiple formulations, it's not so much that the eddy events change in different formulations, it's actually the advancement equations, because you can time advance.
It's the reaction diffusion
Right.
potential.
Right. You can time advance or you can spatially advance. You can run it as shown here and in everything we've shown so far, where it's basically interpreted as Cartesian. In other words, it's a linear geometry. You can also run it with the cylindrical diffusion equations, the radial diffusion equations to represent a round jet. So at the level of the advancement equations between the eddies, there are a lot of variations you can do, depending on the application.
I'm thinking that in this case, if you sweep in this way, if you must have some entrainment. You have the circulation zones outside of the flame.
There's mixing going on. There's mixing going on. As Alan said, when you have stirring events, you actually have transport of scalars and momentum. So there's mixing going on. There's a transport of scalars momentum across the radial or the horizontal line.
But also the recirculation is, of course, an elliptic effect that the model cannot see because it's inherently parabolic.
Instabilities and everything like that, yeah.
But even in the mean sense, recirculation can be generated that the model doesn't see. But there's another aspect of entrainment that is not seen in the. This is, like I said, a time-advancing ODT that's just been sort of interpreted as spatial. If you actually advance if the governing equations that you advance are spatial equations and you advance then the spatial continuity equation, then for example, one case we've done, I have slides where I can just illustrate it, is a fire plume where if you start out with some, hot gas at the base of the fire, it's accelerated, and because in spatial advancement, up here you have a higher mass flux, say. Well, now you're applying the spatial continuity equation. So if there's more mass flux coming out than in, then the continuity forces you to draw in fluid from the side. So the continuity equation induces a lateral inflow, and so the image that you generate when you actually advance the spatially developing equations shows the necking in of the plume. Of course, which happens. You see this in the actual plume. So as this accelerates, the spatial continuity equation then forces a lateral inflow. So in other words, there are other variants of the stepping, the evolution equations in ODT that will capture other effects.
You can also see the growth of the jet as it goes downstream as well. So this is just an explanation. I'm going to go through this quickly. I know it's almost lunchtime. It's lunchtime. This is basically the ODT on a lattice. Okay, and it's sort of similar to the LEM 3D. You have, let's say, we have here, say, a flame of some sort, but you don't have to determine its position ahead of time. But you do have basically a lattice of ODT elements, solutions, that are basically running vertical into the plane and horizontal as well. So it's a 3D lattice. And it's overlaid on the area squared shown here with sort of dashed lines. Okay? And of course, some of these ODT domains are going to intersect at nodes, where you have basically 3 ODT domains crossing each other. Those nodes are important because they're actually an important issue here is when you have 1D solution, you don't see 3D effects. So this is, along these nodes, that's where you can actually channel some of the 3D effects like a large-scale advection. And of course, within the ODT1 ODT solution, you have a higher resolution, albeit in 1D. And of course, you have a coarser resolution in LES. So the way it's done, and I guess this is sort of one way that I did this, is I basically have an LES and an ODT solutions, and they're coupled. The LES solution takes care of the flow. Basically, you have continuity and momentum. And you can pick your choice, although potentially ODT can be used for the LES, for the subgrid scale closure. You can pick any model for, as far as you're concerned for subgrid scale stresses. Okay, so LES governing equations that basically on the coarse grid are used to. They're not designed to do the scalars, unless you choose to carry the scalars. They're designed to do continuity and momentum. And then the ODT equations. Here I'm basically writing here a detailed equation. It does not mean that all the ODT is sort of shown up like this. But what I'm showing here are the unsteady terms for momentum. That's the coupling term. Then species and energy. And then you have here some terms that are resolved on the 1D domain. And some extra terms that you'd like to model or to represent. And some of the key terms here include, for example, the advection term. They include any diffusion, viscous effects, diffusion of mass or heat in coming from the different directions. So X1 would be along an ODT solution, and the other two is X2 and X3 are the normal solutions in the 3D directions. Okay.
So just going to relate to your question, you have that pressure gradient. Now, how would you represent that pressure gradient?
Well, in the mean flow.
It's not the mean.
Pardon me?
It's not the mean flow?
Pressure fluctuations is what he's asking.
Yeah, the pressure fluctuation, it's down through the pressure scrambling. That's what Alan was talking about.
That represents one
You
effect.
distribute the energy, exactly one effect, you distribute the energy among the velocity components
Right.
as a way of
Yeah.
pressure
So
scrambling.
The question now is that this
Yeah.
term is the biggest term in the equation.
Yeah, it
For
drives
small scale is the
Yeah.
biggest term. So how we can keep the term which is not biggest and at the same time to modelize the term which is
The
most
triplet,
important.
the triplet maps are can be seen as modeling the net outcome of the combined interactions of the velocity and pressure fields. So that's the minimal interpretation of what comes out of all that interaction.
So this discussion is a little bit not clear.
It
because
sweeps a lot under the rug.
Yeah.
For me, it's not too much information.
You
That's
can
right.
think of this
That's
as if you can think of it as sort of filtered pressure and fluctuation pressure in a way. You can keep the filtered pressure from the NES solution if you want to. That's what drives all the flow in a certain direction, or I mean in all kind of directions, our scale. And then you can think of the residual term as the sort of one way to think of it, maybe an expression scrambling effect in a sense.
Yeah, the pressure velocity fluctuation ultimately is what controls all the details of the eddy structure in the inertial range.
Yeah.
And we've chosen to wrap that whole big mess
And
into
put
triplet
all
maps,
this information in the first term.
in essence, if you want to think of it that way.
Okay.
Yeah.
So, and the omegas here is, I think, what Suresh called F. These are the stirring events. They are, you can think of them as if you have an unresolved residual term, U prime, and then, for example, for temperature, dt, dx1 or something. That's what the omegas are supposed to represent. So these are sort of like, if I were to take these equations and filter them, I should get my LES solutions for the velocity, temperature, and pressure, and velocity, species, and energy. Okay, but you still have to model these terms. Okay, that's a modeling sort of challenge. You're not doing DNS.
And this LAM just determines the direction of the triplet. It's
For these, which ones?
and this index LAM.
Oh, that's the direction of the ODT
Direction.
domain.
Yeah.
So the ODT domain, I'm calling it 1, even if it's pointing vertical, whatever.
So if here just in one direction. Triplet.
Yes, exactly.
So you don't change the direction of triplets here.
Well, if you have a vertical domain, then it's along the ODT domain. If I have a horizontal domain, it's along the horizontal domain. If I have a domain into the board, into the board, then it's going to be along that direction.
That's like I mentioned, the idea of having three kind of distinct but coupled flow solutions, and each one has the triplets only in the one
Residing
direction,
on it.
but then they couple together to give it more 3D character.
Exactly.
But if you happen to have the x1 direction parallel to the flame front, then the diffusion is not important in that direction.
Well, yeah, but the flame is supposed to be moving around.
So you
It's
have
another
three
situation.
situations.
There's a modeling issue that you sort of have to deal with this, is whether, because you do have some diffusion terms here that show up here, whether you can ignore them, whether you lump all of them and multiply by a factor. There's this effect of statistical orientation of the flame, which you can actually get if you decide to use your solution to get a filtered sort of profile of, say, progress variable or something on the area script.
If there's a region where the flame is kind of getting roughly planar and not a lot of turbulent broadening, then on ODT lines that are parallel to the flame's surface, you won't see that flame. But there's another solution that has ODT directions normal to that flame, so it'll be seen on that other solution.
Normal to statistical normal, because the flame can be moving around.
But I'm saying if it was not so turbulent in
Yeah.
some region,
Oh, okay.
in some region was roughly planar, then it would be missed. ODT wouldn't necessarily capture it fully, but on two of the directions, but the direction normal, like I said, because there are these three solutions. There are these three sets of ODT domains that are simultaneously
Pointing in
evolving.
all
Each array of domains is oriented in one of the three coordinate
So the
directions.
ODT is done in three Exact directions.
And they're stationary in this O'Marian description.
Yeah.
So they're basically running in a fixed domain. So they capture all the gradients potentially, you know.
So if you don't see it on one domain, you'll
You can see
you'll see it on the other.
it.
So one of them will intersect, one or more.
But why don't choose this direction stochastically?
Well, that's, you could say that what Suresh does is sort of doing that, you know, because then you have to have an entirely different coupling. Much of the coupling, like I drew, you know, if you're going to write a coupling algorithm, I drew an example where, you know, there was a compression in the vertical and an expansion in the horizontal. Okay, so that's one implementation. If you want to talk about something that's more stochastic, then you're actually getting, well, the Lagrangian is, what Tarek drew here, I wouldn't call it stochastic. Well, it's stochastic in the sense that the plane is random and it's following it. You see,
But it's prescribed by the still filtered solution.
right, but it does still have the idea that the domain, in other words, here the domains are oriented locally to be normal to the flame brush, okay? But then you have, so then you have to have an algorithm that
Just keeps track of it.
keeps track. And like Tarek said, if you do it this way, then you have to decide if you're premixed or you're
Yeah,
diffusion
premixed.
flame.
Yeah.
We can imagine in any case some equation for direction.
Yeah.
Okay?
Yeah.
It can be
Yeah.
isotopic or some with some preferred direction. We can imagine this kind of equation to add to this.
Yeah.
In fact, you can do both if you want.
Yeah. Well,
You
if
can do
the,
both.
if the preferred direction is chosen to be normal to a flame, then you have to somehow have a pattern recognition that tells you a flame's there, because this model doesn't know about flames. It knows about advection, diffusion, and reaction, which is what DNS knows about.
You
DNS
can
has
push process a solution to get a flame.
DNS has no prior knowledge of flames. It just solves the equations on a grid, and we take the same approach.
And I guess in the LEM, because we just put the LEM everywhere and it detects the flame if it
Right.
shows up.
Right, and in Suresh's approach, you
More
don't even need a
stochastic.
concept of orientation. You know, by definition, it's just
Actually, I'm going to show.
any
if we've got
orientation you like.
I'm going to show a case in which you have a turbulent flame and with stationary WT solution, you still get a wrinkled
Right.
flame.
Yeah.
So anyway, there are certain terms here that need to be modeled. That's just too much detail. So the key thing there, I think, is to really capture some of the 3D effects. And these are done using what I call node advection. And node advection, because I'm going to just skip to the results, is that whenever I have nodes, this is an ODT domain, and this is an ODT domain, and there's an ODT domain crossing it. And then, of course, you have solutions. You grid on the ODT domain here, and you grid on the ODT domain here, is to basically channel advection across nodes first, okay, and then relax the solution between the nodes. It's like almost like a Lattice-Boltzmann kind of approach. Let's say if you want to go to, you know, you live in the street, you want to go to your neighbor here, you don't just jump over the roof, you basically have to follow the main street. So this is sort of a way to channel, because advection is basically just moving stuff, you know, and as long as you move stuff and then moving things correctly, that's all you need as far as modeling these terms. So these are done with what I call node advection. I basically solve the solution here, knowing that I have all the components for this term and this node, and then I generate a solution here, this node, and then I can relax the solution in between by just solving one-dimensional advection equation. So that's all I'm doing. So based on what happens in terms of the solutions here, I can pass the information between. And this is sort of an alternative way to, for example, splicing, or to, so this is large-scale advection, or to the LEM3D sort of approach to this suggestion.
And I think an important point here is that you were saying, how can you improve the models? Like I said, there's triplet map, the eddy event, the rate expression.
And that's only the eddy part of the UV part.
Yeah, those parts are kind of, I think, fairly, those formulations are fairly converged. But things related to both the diffusive advancement, and here Tarek shows, a different set of equations than what I wrote down, and especially the domain couplings, and the way they evolve globally, is subject to all manner of possible alternate
It's like modeling. It's a modeling challenge like everything else. But the idea is that if I have to write these are like DNS-like, and I have certain terms that are resolved, and other terms that I need to model, what do I need to do to make them look like a DNS-like solution? They're not DNS, but how do I model all these terms so that when I filter my solution, I get a right filtered LES solution? That's the sort of the idea. I just wanted to show one result of sort of homogeneous, non-homogeneous ignition. Basically, I'm starting here with hot blobs of lean fuel and oxidizer, and cold blobs of mainly fuel. So the blue would be lean, the red is going to be rich, and the air or the oxidizer is going to be heated, and the fuel is cooled. So this is a non-homogeneous mixture. It's basically made up of, does not have basically a slab of fuel and a slab of oxidizer, or a full mixed homogeneous mixture. It's a non-homogeneous mixture. And this is sort of compared with the DNS, and this is sort of a really sort of coarse solution just to test the problem. And I'm also running, different Lewis number effects. Where the energy resides is barely inertial for the coarse solution, non-cube, and within the inertial range for the sort of, this is essentially 16 cube. Okay. This is what you get with just looking at the ODT solutions and filtering them on the 3D domain. So this is our 3D domain. This is basically, I think, this is a 9-cube kind of solution. So these ignition kernels that you see there are from the ODT solutions, basically just filtered. And of course, they are below the LES grade. This is what I meant by outliers. These are things, although you may have the same mixture, different dissipation rates generate different ignition delays. So when things happen, depends upon the local dissipation rate, which is not resolved by LES, but it's resolved by ODT. So you have a bunch of these ignition kernels, early ignition kernels. Eventually, some of these ignition kernels will grow. And then new ignition kernels, because based on the delay due to the dissipation rate, will also grow. Okay. Again, this is ODT solutions. So these are basically lattices of ODT solutions in sort of 3 directions. And then you filter those solutions, and you're getting that. And then the kernels will grow. They grow further. They start to interact. They start to merge. Eventually, the whole thing will be just just hot gases and no flame. Okay, this is just the progress variable, meaning if it's 0, it does not burn. If it's 1, it's fully burnt, and I'm taking a value of 0.5. So behind it, it's fully burnt. Behind, inside these kernels, and outside it, it's not burnt.
The filtering was done for the graphical rendering. It's not part of the algorithm.
No, it's not part of it. It's post-processing.
It's just post-processing.
It's just to show.
Not filtering during the advancement.
Exactly. And this is basically showing you have outliers here that in statistical distribution, you'll have to capture these things and the local conditions in which the ignition occurs. And what you have here is actually lean premix flames evolving into richer premix flames. So this is sort of changing within the mode of non-premix, from lean premix to rich premix. And somewhere down the line, you can actually cross even boundaries of non-premix flames. So you have actually different modes and the transient process being captured as well.
Is it a constant volume simulation?
Yeah, this is constant density, constant volume kind of simulations.
Is it not constant density?
I'm running at constant density here.
Yeah, constant density. But you have the density variations.
No, I don't. For this problem, I'm just showing it with constant density. The reason why I wanted to do that is because I wanted to see to basically decouple the effects of turbulence and chemistry. So I wanted to run this problem with constant density. Because one of the things I'm trying to do also is I wanted to run different Lewis numbers. And, yeah.
It's pretty initial temperature sensitive.
You mean the highest temperature or the lowest temperature?
What are the initial temperature you have?
Well, I'm basically saying one is preheated to ignition conditions, near the lean conditions, and then the other one is very cool, like room temperature. And so the ignition will actually start at very, very lean conditions because of the preheat. And then so the kernels, where the ignition occurs first, is very lean, fuel lean conditions, high temperature and low dissipation rate. If it's high temperature and high dissipation rate, you get delay. Okay? And that's why you're getting some delay in the kernels here. Now, if you were to run the DNS and filter the DNS, you will see some similarities and some differences. Because this is a statistical model. It's designed to produce a statistic, not the actual filtered DNS, of course. Because no LES is going to be filtered DNS no matter what you're going to do.
Was it Hobbs and Jackie did this case, similar to that case?
I did this with hydrogen.
You did the
With
DNS.
DNS. Yeah.
And then you compare it to that DNS.
Well, no, this one is actually, I did my own DNS, constant density, different Lewis numbers, so that I can see also the Lewis number effects.
I said, and then you compare the ODT results.
Yes, with DNS. Exactly. And, you know, this is a comparison of some volumetric effects. Different Lewis numbers. Some of the interesting thing here is when you have the different Lewis numbers, you know, heat and mass dissipate away from kernels at different rates. So if you have heat escaping faster, you may actually delay the ignition, but then you delay it, but then when the ignition occurs, you can basically heat the next layers at sort of a faster rate. So there's a kind of a really fundamental sort of differences between when you include those number effects, what happens to the kernels. By just playing with the lowest number, you can see different delay rates as far as the mean progress variable.
Just a comment. We did some similar DNS with hydrogen, of course, non-unity Lewis number. We found that if you have ignition, Lewis number may not be that important if you couple everything, because you have a very fast propagation rate. Ignition front.
Yeah.
So fast that diffusion is not very important.
It depends upon what you're diffusing, for that matter. If you, for example, if you have hydrogen, and you may have some initially some H forming in the kernel before you get to the ignition, if that H forms a peak, and then that's a fast diffuser species, you may actually deplete the kernel and delay the ignition a little bit. But also when you talk about mass and heat, you also have other issues as well. Because if you get a hot kernel here, and the species are not diffusing as fast, but the heat is diffusing fast, you're passing the information to the next layers that, hey, it's time to ignite. But if you do that, it's different than if you shield these kernels and make them hotter, and then eventually they evolve into even more faster propagating kernels.
There's also a Teradonic mechanism. You have a ignition, you don't have a really much diffusion, but you have ignition difference because you have temperature, you don't have temperature difference, but you have species difference. So the ignition delay time is different, and then they ignite sequentially. In that mechanism, the diffusion is not important.
Yeah, the hydrogen stuff we saw, but I think it depends upon the fuel you're using as well. I'll just skip one example here, which is the case of premixed. I'm hitting it with a really high turbulence with two flames initially parallel to each other, and then as they're propagating to each other, they start to interact and interface, and you have mutual annihilation going on there. And so this is a DNS, and then I'm following it with ODT. So this is the filtered DNS looking at sort of cuts of the two pairs of flames as a function of time. And this is the corresponding ODT solution. Okay? ODT, without really having a G equation, without having any track and film track algorithm, it actually has the ability to wrinkle the flame because I have the mean advection, large-scale advection as well built into the solution. So you see the flame wrinkling, and sort of these are sort of different resolution, 32 and 16, and then eventually the flames start to interact and then annihilate. Okay? But before that, when you do filtering of two solutions where you have actually within the same box two flames, you can see some local increase in the amount of heat release rate because you have two flames, not just one flame.
The two of them pretty similar in their particular details. in the beginning, and they just gradually get like distinct. Yeah.
Because you have turbulence. You know,
Right.
turbulence is not symmetric in that case.
Oh, okay. Because you started kind of from a
It's planar planes.
okay. Did you start the ODT from like some non-planar, like turbulence initial conditions?
Yes, yes.
Oh, okay, so that turbulence at t equals 0.2, a lot of it was already baked in the initial condition.
Exactly.
But later it's able to depart, and at t equals 0.6 they look just different shapes. Yes.
Exactly.
Okay.
So even with a coarser resolution, you can see some differences. A filter DNS is not a filter, is not an ODT, LES ODT. Okay? But what's important here is if you look at the statistics, how, for example, fast the area, the flame area growth occurs, you can see some similarities. Okay? And if you look at statistics of curvature, mean curvature, you also see some similarities. You know, I'm showing red and blue that correspond to the DNS and the ODT. So statistically, the model works, and you know, on the case by case, of course, it's not gonna work exactly. But that's expected. 1D solutions, they're not the same as filled boxes everywhere with LES. Just briefly here, I talked about Lagrangian formulation. I dropped all the extra terms that are associated with the advective terms here. And this is work that is going on in progress using the FDS code, the Fire Dynamic Simulator code. This is just a fire plume with all kinds of instabilities. And then basically here I'm embedding ODT solutions on it. And of course, there are some different challenges here when you do this, because occasionally you're going to get some lesions where you may have some bolt spots which you can spawn or move some ODT domains. It's basically a Lagrangian solution with all the sort of challenges of a Lagrangian solution. And it's really cheap. This problem, I think, is like 0.2 meters and 0.6 meters. Okay, simple chemistry, but this was run in a couple of hours. Okay, and this is sort of work in progress. So, attached flames, cheaper, but you sort of have to commit to the fact that you actually are tracking here stoichiometric mixture fraction contour, and you attach flames on top of it.
It's surprisingly good. So your ODT have to consider the buoyancy.
It's got, yeah, but locally, there's no. Locally, what you're doing is the flow.
Yeah.
The flow is, there's no, basically the flow is the one that the ODT domains remain normal to the flame, and all the aspects of the flow and forces and everything are basically dropped out. So locally, you attach the flame to normal to the flame and let it be advected. So if you have mean motion here because you have a flow, the ODT domains are going to go like this. And then guess what they will do here? When they get to the tip here, what do? They're not going to be kicked out because they're tracking the flame. They may actually just sit there. Because they can't leave the flame. They just sit there and you sort of have to move them. That's it. They made it to their terminus, to their bus terminus, and they have to be taken out and be replenished with the ball.
If you look at the smaller scales, basically, if you can talk about an Eddy Richardson number, the smaller eddies basically don't feel the buoyancy nearly as much as the shear that they feel. Of course, at the larger scales resolved in the LAS, you have to be treating the buoyancy, but it's at least you can make at least a plausible case that at the scales of the ODT, you don't need to put in the buoyancy necessarily. I mean, it's case by case. You have to consider it.
There's always approximation in a sense.
It's very impressive.
I think I'm done. I'm not really apologize for saying this.
Anything else that you should address, or should we break up for lunch, or do you have questions?
It's very nice to give us a lecture because I'm really interested to try.
Sure.
And we have all these individually we can talk, and if you have any questions.
Yeah, we have questions we can contact me by email.
Oh yeah, definitely. Sure.
So this was actually the last session here, right?
Yes,
So then tomorrow it's the conference, and that's the KTH.
that's right.
Oh, that's important. I
Yeah.
don't know where it was.
Where is that? So that's on main campus, KTH campus. I sent an email out with the room number, which is
Building, so it's not here.
it's not here. No, I hope we will have some signs out there. So
Is it near where the metro comes out?
it should be pretty close to that. Yes, yes.
It's in the main building.
But the thing is that it will start, of course, at 1:30,
Okay.
and many of us will be here anyway, so we'll walk from here to over there.
Yeah.
But if you,
So we'll have lunch here tomorrow, right?
we have lunch here tomorrow, yes.
Yeah. Will
we
be
have
afterwards lunch over
And
there.
then we have tickets for lunch over there for the 2 days on the other 2 days, yes. We also will have an informal reception after the first day, on Wednesday, that is tomorrow afternoon. And that will be here in this building,
Oh,
not even in this, either in this lecture room, or if the weather is good, of course, we'll do it outside this building and stuff. But that's to be seen how the weather is tomorrow. In any case, wine and beer is already ordered.
But how about the weather?
well, then we'll be indoors if the weather's good.
Did you order the weather?
So tomorrow it starts only in the afternoon.
Yes,
Oh, okay.
that's right, yes.
So if you give us a map or something.
Yeah, I will have the Google map. I will send you the link.
But also, I mean, if you are here before lunch, you can go all together. And
Yes, yes.
Yeah.
I can, the current program is, you can see that at the end of the so-called informal schedule on the web. You go to the conference of our page. There is on the second item is the informal list, which has all the titles except for the one of Laszlo's. That one is not. So Fox has not been a title. Everybody else is now a title. If you have suggestions regarding the program, which is still informal, please let me know as soon as possible. And otherwise we'll be, so I'll send an email, and otherwise we'll have the official thing then again tomorrow.
Okay. And you mentioned earlier the Thursday that there would be a dinner or something? Or?
Yes, there's a dinner on Thursday. That will be here in Albanova.
Oh, okay.
And